I'm Manwu. In this project, my partner Shuwen Wang and I will talk about a new deep learning NLP method. Open world learning has become a popular research topic in natural language processing. Traditional classification task only focuses on closed word learning, where the classes are predefined in the training data. In open world classification problem, the model is to not only recognize objects belonging to the classes already seen before, but also detects new class samples which are previously unseen. In recent years, there are many novel methods proposed to deal with open world learning problem. Today in this paper review, we are going to introduce a novel model which employs open world learning into graph structure data. We will introduce this paper from the following 5 aspects. My partner Shuwen will introduce the introduction, related work, and experiments part. I will give a detailed review of the methods part, and finally I will conclude this paper.
Existing solutions to open-world learning can't be directly applied to graph structured data because they cannot model graph structural information. Here is an example of open-world learning for graph node classification. Given a graph with some labeled nodes and unlabeled nodes, open-world graph learning aims to learn a classifier to classify unlabeled nodes belonging to same classes into its own class, and also detects unlabeled nodes not belonging to any same classes as unseen class nodes. This paper proposes to study open-world learning for graph data and wants to deal with 2 challenges. And there are many learning frameworks to deal with graph data. The most famous are JSON and JAT. However, they may have some limitations. These existing methods mainly carry out the learning in a closed world setting, where nodes in the test data must belong to classes already seen in the training data. As a result, when an unseen class node appears in the test set, classifiers can't detect it and will misclassify the node as seen classes in the training data. However, in reality, new trains are constantly emerging, and a model that cannot detect these new trains can hardly work well in a dynamic environment. This phenomenon is called the open world learning problem. To date, open world learning has already attracted many interests from natural language processing and computer vision fields. For example, in NLP, the model DOC proposed the solution to open world learning by setting thresholds before the sigmoid function to reject unseen classes. In computer vision, the work of towards open world recognition studied the problem of recognizing unseen images that are not in the training data by incremental learning. However, to the best of our knowledge, the open world learning problem has not been studied in graph structured data and graph learning tasks. Currently, existing solutions to open world learning cannot be directly applied to graph structured data because they cannot model graph structural information. Here is an example of open world learning for graph node classification. Given a graph with some labeled nodes and unlabeled nodes, open world graph learning aims to learn a classifier to classify unlabeled nodes belonging to same classes into its own class, and also detects unlabeled nodes not belonging to any same classes as unseen class nodes. This paper proposes to study open world learning for graph data and wants to deal with two challenges. Challenge 1: how to design an end-to-end framework for open-world learning in graphs, where Anson class has no labeled samples and may exist in an arbitrary form different from some classes. Existing graph neural networks are typically built based on the closed world assumption and cannot detect Anson class. Challenge 2: how can we model the uncertainty of node representations and promote robustness in graphs? Many existing GLM-based approaches only generate deterministic mappings to capture latent features of nodes. A major limitation of them is their inability to represent uncertainty caused by incomplete or finite available data. To overcome the above challenges, this paper proposes a novel open-world graph learning paradigm for node classification tasks. For challenge 1, they employs two loss constraints, a label loss and a class uncertainty loss, to ensure that the node representation learning is sensitive to Anson class and help our model to differentiate whether a node belongs to a Sun class or an Anson class. For challenge 2, instead of learning deterministic node feature vector, they utilizes a graph variational autoencoder model to learn a latent distribution to represent each node. During the classification phase, a novel sampling process is used to test the certainty of a node belonging to a Sun classes and automatically determine a threshold to reject nodes not belonging to Sun classes as Anson class nodes. Next, my partner Man Wu will introduce their proposed methods and the experiments.
This is the overall framework of this paper. The input is a whole graph with enabled and unlabeled nodes. The framework for open-world graph learning mainly consists of two components: node uncertainty representation learning and open-world classifier learning. In the testing phase, they propose a novel sampling process to test the certainty of the seen nodes and determine a threshold to reject unseen nodes. For each part, I will give detailed descriptions. As mentioned before, a major limitation of most GCN models is their inability to represent uncertainty caused by incomplete or finite available data. In order to encode latent feature information of each node and obtain an effective representation of uncertainty, they employ variational graph autoencoder network to generate a latent distribution based on extracted node features. This network consists of graph encoder model and graph decoder model. The graph encoder model utilizes a two-layer GCN. Given the input feature matrix X and adjacent matrix A, the first GCN layer generates a lower dimensional feature matrix through equation 1. For the second layer GCN model, instead of generating a deterministic representation, they assume that the output Z is continuous and follows a multivariate Gaussian distribution. Here they follow an inference model in equation 2 and 3. Mu is the matrix of mean vectors mu I. Sigma is the standard variance matrix of the distribution. Then latent representation Z can be calculated through equation 4. After obtaining the latent variable Z, a decoder model is used to reconstruct the graph structure A to better learn the relationship between two nodes. Here, the graph decoder model is defined by a generative model in equation 5 and 6. Aij are the elements of A. After the variational graph decoder network, each node can obtain the uncertainty embeddings, and it consists of two parts, labeled nodes, Z-labeled, and unlabeled nodes, Z-unlabeled, to better learn an accurate classifier for classifying both seen and unseen nodes. This model consists of a cooperative module, a label loss, as well as a class uncertainty loss, working together to differentiate whether a node belongs to a seen class or an unseen class. The label loss is to minimize the cross-entropy loss for the labeled data. Here, Fs is a softmax layer. NL is the number of labeled nodes. C denotes the number of seen classes, and YIC denotes the ground truth of the ith node in the labeled data. YIC hat is the classification prediction score for the ith labeled node Vi in the C class. Since there are no class information in the test data and there has a considerable number of unseen nodes, the class uncertainty loss is proposed to balance the classification output for each node and have superior effects on the unseen nodes. In the paper, an entropy loss is placed as a class uncertainty loss, and its goal is to maximize this entropy loss to make the normalized output of each node balanced. In equation 10, Nu is the number of unlabeled nodes. In addition, in the node uncertainty representation learning process, there has the VGAE loss. The first term is the reconstruction loss between the input adjacent matrix and the reconstructed adjacent matrix. The second term is the KL divergence. The label loss, class uncertainty loss, and the VGA loss are jointly optimized by the objective function, and all parameters are optimized using the standard backpropagation algorithms. In the testing phase, a novel sampling process is proposed to test the certainty of a node belonging to seen classes and automatically determine a threshold to reject nodes not belonging to seen classes as unseen nodes. The detailed process is in this figure. After performing the node uncertainty representation learning, a distribution of the node embeddings can be obtained. Thus, for each testing sample, generating m different versions of feature vectors from this. Then feeding these m different representations into the softmax layer to turn them into probabilities over C classes respectively. In this example, there has 4 seen classes. Then through the softmax layer, m probability output Si can be obtained. Then the probabilities of each class are averaged to obtain a vector SIA, and choosing the largest one, max SIA. In the first example sample, the largest one is 0.63. There is a formula to recognize whether this node belongs to the seen or unseen class nodes. If max SIA is less than or equal to a threshold T, rejecting this testing node as a sample from the unseen class. Otherwise, its predicted class is the one with the highest probability. Here is a class 1. So, in open world learning, a key problem is the determining of the threshold T. In the paper, a selection approach is proposed to automatically determine a threshold to reject nodes not belonging to seen classes, specifically using the validation set to do the threshold selection. Similarly, for nodes in the validation set, performing the node uncertainty representation learning, and conduct the same sampling process and choosing the largest probability. Then average these chosen largest probabilities of all the nodes and obtain AVGC. Because unseen class instances are assumed not appearing in the validation set, choosing 10% nodes with the largest entropy as the expected unseen class nodes, and compute their average probability denoted as AVGE unseen. The final threshold is calculated by averaging these two probabilities, AVG seen and AVGE unseen. In the figure B, applying the determined threshold to the test set, and we can observe that the threshold obviously differentiates the seen and unseen class instance. Next, Shuwen will introduce the experimental details.
The experiment part. They employ three widely used citation network datasets, Cora, CiteSeer, DBLP for node classification. For each dataset, they hold out some classes as the unseen class for testing and the remaining classes as the seen classes. They randomly sample 70% of nodes for training, 10% for validation, and 20% for testing. Note that the nodes of unseen class only appear in the testing set. They use the validation set to determine the threshold for rejecting the unseen class, and they use the macro F1 score and accuracy for evaluation. To make a fair comparison and evaluate the effectiveness of their design, this paper selects the following baselines with necessary adaptation. Here, DOC is the state-of-the-art open-world classification method for test classification. This is the experimental results on Cora and CiteSeer with different number of unseen classes. The Open WGL model achieves the best performance among all baseline methods of the three datasets. They also report closed-world learning setting results without the unseen class. The results show that when networks do not have unseen class, OpenWGL has comparable performance as JCN, confirming its effectiveness and generalization for node classification. In addition, they conduct experiments to compare variants of OpenWGL to demonstrate the effectiveness of the class uncertainty loss and the impact of the VGAE model. Results show that each component can lead to performance improvements. And they also do the parameter analysis to explore the impact of feature dimensions of node output embeddings. In the case study part, they also report the confusion matrix of OpenWGL on Cora network to demonstrate the superior performance of the model. Finally, my partner Man Wu will give the conclusion of this paper.
This paper studied the problem of open-world graph learning and argued that most existing graph neural networks are based on closed-world setting. The paper proposed an uncertain node representation learning approach by using label loss and class uncertainty loss to constrain variational graph autoencoder to learn node representation sensitive to unseen class. The paper proposed to use a sampling process to test the certainty of a node belonging to seen classes and automatically determine a threshold to reject nodes not belonging to seen classes as unseen class nodes. Thank you. This is all the content of our paper review.